Hi everyone, and welcome to my Basics of Flight Mechanics class. So today we're going to be covering the first step leading to the 3 degrees of freedom, equations of motion. And as a reminder, it is a mathematical description of how an air vehicle moves about in the atmosphere in the vertical plane only. If you wanted to get the whole picture, you would have to establish the 6 VOMs. So this class is based on fundamentals of airplane flight mechanics, and it is a book I would highly recommend if you're starting out in aerospace. The first thing that I want to talk about today are the different reference frames used in aerospace. So this book uses 4 of them, and that is the ground frame, the local horizon frame, the wind frame, and the body frame. Now, depending on which book you use as a reference, the number of reference frames may vary, and their definition may vary a little as well. The reason why we use different reference frames is because different vectors are defined in different reference frames. It just is more convenient to do so. Now, when we're going to be establishing the EOMs, we're going to need to add these vectors, and because we can only compare apples to apples, you can't add a vector defined in a reference frame with another vector defined in another reference frame. So eventually, we're going to need to resort to something called rotation matrices or transformation matrices, and that will essentially transform a vector from its original frame to a common frame so it can be added up. The ground frame is often called the inertial frame, and it probably is the most important frame because it is the only one where F is equal to ma stands without any adjustment or additional terms. Everything will be expressed in relation to the ground or inertial frame. It is fixed to the ground, its x-axis is going to be pointing north, its y-axis will be pointing east, and the z-axis is going to be pointing down to the center of the planet. Now, a number of assumptions need to be made for that reference frame to be considered inertial, and that is that the Earth is flat, non-rotating, and non-accelerated. The local horizon frame is essentially an inertial frame attached to the center of gravity of the aircraft, so it is going to translate with the aircraft, but it won't rotate with it. It is going to remain parallel to the ground frame, and because it is attached to the aircraft, it is often called the vehicle carried frame. It will be angled with respect to the wind frame by the flight path angle. The wind axis system is also attached to the CG of the aircraft, but its x-axis is coincident with the velocity vector of the aircraft. So essentially, it is tracking the trajectory or flight path of the aircraft. So if you're dealing with a book that is describing the 6 VOMs, the wind axis system is often used to account for the angle of attack alpha and the side slip angle beta. In this book, however, we're dealing with the 3 VOMs in the vertical plane only, so there is no beta. It is here to account for the flight path angle gamma. Essentially, it is a local horizon reference frame pitched by the flight path angle gamma. It is also the primary reference frame to define aerodynamic forces, and in this book, it is used to express the equations of motion. The body frame is also attached to the center of gravity of the aircraft, and it translates and rotates with it. So whatever the aircraft does, the body frame will do as well, and you will notice that in many books, the equations of motion are expressed in the body frame. It is angled with respect to the wind frame by the angle of attack alpha when dealing with 2-dimensional motion. So now that we've defined our reference frame, we're going to need to talk about something called transformation matrices. When we're going to be establishing our equations of motion, we're going to need to derive our sum of the forces, and that is basically vectors being added up. And to be able to do that, you need to be able to transform them from their original frame to a common frame so the math can actually work out. So in this case, the transformation that we're interested in is between the local horizon frame and the wind frame. So we're going to have to go through a single rotation by the flight path angle gamma, the angle between the local horizon frame and the wind frame. So we're starting with our unit vectors IH and KH, and that is representing the local horizon frame, and we're going to be rotating that by an angle gamma to yield our wind frame materialized by the unit vectors IW and KW. So essentially what we need to do is to project the old unit vectors onto the new frame, and that is both IH and KH onto IW, and both KH and IH onto KW. So the projection of IH onto IW is going to be cosine of gamma IH. And because the projection is pointing in the same direction as positive IW, it is going to be a positive contribution. The projection of KH onto IW is going to be sine of gamma KH. And because the projection is pointing opposite to the positive IW, it is going to be a negative contribution. So the projection of KH onto KW is going to be cosine of gamma KH. And because the projection is pointing in the same direction as positive KW, it is going to be a positive contribution. Finally, the projection of IH onto KW is going to be sine of gamma IH, and because it is pointing in the same direction as positive KW, it is going to be a positive contribution. So this is what you see on the left. IW is equal to cosine of gamma IH minus sine of gamma KH, and KW is equal to sine of gamma IH plus cosine of gamma KH. So now we have enough to construct our rotation matrix, and all you need to do is to multiply the vector components expressed in the local horizon frame materialized by x of h, y of h, and z of h to yield the new vector components in the wind frame materialized by xw, yw, and zw. Now, the last thing I want to talk about today is the wind frame rotation. We're going to need to derive our inertial acceleration to derive the equations of motion. And because the wind frame is actually rotating with respect to the local horizon frame, we somehow need to capture that in our derivation, as there's going to be a normal acceleration component in the inertial acceleration equation. And to account for that, we essentially need to take the derivative of IW and KW. So all you need to do is to go back to these equations on the left where we have IW and KW, and you need to take the time derivative of these equations. So when you take the derivative of the first line, you're going to get the second line. All you need to do is to factor out minus gamma dot, and you will see that what you have in parentheses is actually exactly equal to KW, and this is what we found here. And now finally, you apply the exact same method to take the derivative of KW. So the derivative will yield the second line. You will factor out gamma dot again, and you will see that what you have in parentheses is actually exactly equal to IW, and this is what we had found here. All right, this is it for today. Thank you very much. See you next time.